Well, good morning, everybody, and welcome to the second of today's webinars from Smart Vision Europe. This time we're looking at regression techniques in SPSS. This is a natural follow-on from our previous webinar where we were looking at correlations and correlation coefficients, how they're calculated and how they're interpreted. If you haven't joined any of these sessions before, I know that many of you have, and you're used to attending them. But if you're new to it, then you should know that the sessions are recorded, so you'll be able to listen to it again afterwards. You'll also be able to get a copy of the slides. We'll email out a link to you after the session's ended. You can download those materials. And if you think it's useful for colleagues who are unable to attend today and you can get enough of them together, it may be possible for us to arrange a rerun of the session. The best thing to do is just send us an email and we'll see if we can do that. Now, with regard to asking questions, all the lines are muted, so we can't actually hear you, but we ask you to use the chat panel. However, if we run out of time, we will follow up with you offline afterwards. And we are used to people on a regular basis sending us emails afterwards and asking us questions. So please don't feel intimidated. Just go ahead and send us an email. We'll be happy to help as and when it occurs to you. If you don't know who Smart Vision are, we are a technology company. We're a gold accredited partner to IBM and also a company called Predictive Solutions and Data Robot. And we specialize in statistics and data science and machine learning and AI and big data technologies. We do work with open source technologies such as R and Python. We're a small organization, but we're made up of a team of people who have a lot of deep experience working in the analytical software world, technology world, more than 30 years on a lot of occasions. And we've all worked for SPSS at some point in the past. So we're very familiar with the SPSS product line. And I've worked for SPSS and SAS and IBM as a consultant. That just basically means we've got a lot of experience of applying these types of techniques, such as regression, that we're going to talk about here, across many different applications in many different sectors, both not-for-profit and public sector. So today we're talking about linear regression and logistic regression. We're going to give you an overview of regression techniques. And we're also going to touch a little bit on correlation again, because we can't assume that people have attended that session earlier on. And then we'll move on to performing a simple linear regression and walking you through the output and how to interpret that output before we make it slightly more complex by adding in extra fields to make it a multiple linear regression. And then at the end, we're going to switch tact entirely and move to using logistic regression and how we interpret that, but to predict a response probability. So a very different situation where we're trying to predict, instead of a continuous scale outcome, a numeric value outcome, we're actually going to try and predict a category outcome and use logistic instead for that. So the first thing we need to address is the term regression, what we mean by regression. So regression is a generic term, and it refers most importantly to a family of statistical techniques. There are many different types of regression methods out there for people to use. Um, so when people say I've used regression, all that they usually mean linear regression, and they kind of assume that you know that, but you just need to be aware that regression, there's lots of different forms of it. There's logistic regression, there's linear regression, there's quantile regression. There's these lots and lots of different flavors of regression, non-linear regression. So linear regression is used when the outcome is continuous to scale in nature, and the relationship between the fields can be described using straight lines. That's generally how it's used. It's kind of like the granddaddy of all predictive techniques. The quadratic regression is a modification of that, and it's a variant of linear regression. It's also used when the outcome is continuous, and but it's also most importantly used when the dependent variable, when the relationship with the dependent variable is curvilinear. So it's not a straight line relationship. And this, you'll find these types of relationships exist in the natural world, so in biomedical data, but they also exist in engineering data when you're looking at things like petrol consumption or something like that against the engine size. And there's lots of variants of non-linear regression that we also have recordings of on our website. Logistic regression is probably the second most commonly used type of regression after linear regression. And it's used when you're trying to predict not a continuous outcome, but trying to predict a category outcome. And if you're using a two category outcome, it's called binary logistic regression, like a yes, no or respond did not respond, or paid back or did not pay back, if it's used in something like uh, debt debt prediction. That's called binary logistic. If it's got more than two categories, if it's like low, medium, high, or something like that, or three different category outcomes, it would be multinomial logistic regression, which is slightly more complex. Poisson regression, again, that's another variant of linear regression. It is used when the dependent variable records counts of events. So, it's used a lot in insurance, where people, you're looking at how many times somebody might make a claim on a policy over the lifetime of a customer, over the lifetime of a policy, or the number of visits to an institution, over time visits to hospital or visits to the theater or something like that. Poisson regression tends to be used in those situations because that tends to have a slightly different distribution. These types of what we call count events, tend to have a slightly different shape of distribution than the types of procedures that linear regression, types of application to linear regression is used against. So again, lots of different variants of regression there. So where are regression techniques used? Well, particularly things like linear regression. They might be used in modeling the relationship between promotion spend and revenue. When we spend a lot of money in marketing, we expect to make more money. We expect to get more money and more sales in. So you could model that and say and try to figure out for every extra $100 I spend on marketing, how much revenue do I actually generate for that? You might be estimating pollution levels following heavy rainfall. So you'd be looking at the amount of rainfall in the previous day, in the previous week, in the previous month over time, the volume of that, and then estimating the level of pollution that one would expect in a given area. You could be looking at predicting tourism revenue based on exchange rates and air travel costs. So you could be looking at a particular region. And tourism revenue is sensitive to things like air travel costs, and exchange rates. If a currency becomes too expensive, and if air travel becomes too expensive, tourism revenue does tend to go down. Tourism numbers tend to go down for certain countries and certain regions. Predicting student test scores based on previous test results and how the peer group is performing, how the rest of the class is performing. You often do a reasonably good job of predicting the likelihood of, or predicting, estimating what some of these test scores are likely to be. Estimating website hits based on retweets and follower numbers. So a lot of stuff around social media and promotion, and how much follower numbers or resharing of social media actually has an effect on people visiting websites or making purchases of a particular product, or viewing a particular video or something like that. And even things like predicting sales of goods based on weather, such as predicting barbecues based on temperature forecasts. These are all typical areas where regression might be used. And as you can tell, that they're pretty varied. It's a pretty eclectic mix. They all have certain things which in common, which is that they're trying to predict a continuous outcome, and they're trying to predict using variables or fields which are independent of that continuous outcome. They might be related to it, but they're kind of independent of it. So regression is a term that comes from a longer term, which stands for regression to the mean. So regression to the mean means falling back towards the average, and the mean that it's referring to in this case tends to be a regression line. So it's the idea that things have an average value here. So here we have public percent reliant on public health care. So this is each of these points is actually a US county. A lot of US counties here. So what percent of the people in each of these counties is reliant on public health care, not private health care? And what is the percentage of people who are unemployed in that? What we're just finding is, of course, that the higher proportion of people who are reliant on public health care, the more they're likely to be, the higher proportion of people who are unemployed. So the regression to the mean here, the averages, is the average that this relationship expresses. And that average is sometimes referred to as the line of least squares. And this is a line which is drawn through the cloud of points in such a way that it minimizes the difference between each of the points in the line itself. So, if we were to manually put this line through the scatter plot here, it'd be very onerous procedure to have to do it. But if you were doing it totally manually, you'd be trying to minimize the distance between each of the points, and the line itself. And if you did that, you'd find that the line, yeah, was drawn in this way. That's how the line is drawn. The differences between the points and the actual line itself, which is a kind of average value, is referred to as the residuals. So these are the residual values. The error, sometimes called the errors, the difference between the points. So the regression line is drawn in such a way that this is minimized. If we added all of these values up, the minus numbers and the plus numbers would cancel each other out and we'd get zero. So as a result of that, we tend to square the differences. So -2 becomes 4 and -3 becomes 9. +2 is 4 and +4 is 16, that type of thing. You square them and you add them up, and that's why it's called the line of least squares. And if you can minimize that number, make the total amount of squared values as small as possible, then you'll know you fitted the line through the points in such a way that you've minimized that you've minimized that number perfectly. Now, the key here is that this line is kind of average. It's called an average relationship here, and we have to be careful because straight lines can't see curvy linear relationships. It is, after all, a kind of average, and you could find that you get exactly the same fit, the same correlation, if you like, the same fit value, irrespective of the relationship. So the point is, we should visualize the data beforehand. I showed this in the previous webinar session. This is called Anscombe's quartet. Every one of these relationships here has the same strength, the same linear strength, even though the relationship looks very different from one another. So be careful, because straight lines can't see curvy linear relationships. They kind of assume that the relationship is linear in nature, and they may not adequately describe the data or fit the data. They may not necessarily describe what's happening. Now, the way in which we measure the strength of the relationship between one field and another field, here we had percent unemployed against percent reliant on public health care. And we've got our line of least squares here going through that. We're trying to measure how strongly these two things are related to each other. Is we normally use something like a correlation value, which we talked about in the previous session. The correlation value runs from -1 to +1. And the closer it is to those extremes, to +1 or -1, the more linear the relationship is, the more perfect the relationship is. A value of 1 would mean that the same variable was effectively correlated against itself. And the value of 0 would mean that there was no relationship between the two factors at all, or at least no linear relationship between the two factors at all. You might actually get a really strong non-linear relationship, like an N-shaped or an arch-shaped relationship, and that line of least squares wouldn't be able to see that, so it would come out flat as a pancake, and as a result of that, the correlation would be 0. The correlation value could be a negative correlation, -0.7. Here we have a strong negative correlation. It could be a strong positive correlation. Here we have horsepower against vehicle weight. Each one of these points is a vehicle, a car. Um, in regression, it doesn't really pay attention to the whether it's positive or negative in terms of the fit values that it produces, and we'll explain why that is the case. But suffice to say, we want to be able to build models that have good, strong correlations in them, and which because that will help us produce better predictions. Obviously, if the two variables correlate strongly with one another, if barbecue sales correlate strongly with weather, with the temperature or something like that, then we want that because it'll help us predict one from the next, and help us predict how hot it needs to be in order to sell X number of barbecues. So you can get these correlation values where they're very close to 0, and that could be simply because the relationship is random. And you can also get strong correlation values even when the relationship is not linear, such as this curvy linear relationship here. So again, the importance here is to explore the data beforehand, do scatter plots, look at the relationships between the variables, make sure you're familiar with them really before you do any analysis, so that you can spot whether or not things are curvy linear or not. And if they are curvy linear, there might be things you can do about that. You might, for example, break it up into two different groups. Say, okay, I'm going to split this into two different groups. You might transform the data in some way. In order to create this chart here, I had to square miles per gallon. So this is miles per gallon squared to create this chart. So one of the things that that analysts do is they take square roots of variables in order to straighten out the relationships, or they often take logs of variables, and that is to linearize a relationship. They transform the data in this way to linearize a relationship so that it's easier to interpret, it's more reliable to interpret the results of the linear regression because we've forced the relationship to be linear. Now, with correlations, it turns out that we can convert all correlation values into a number called a R-square value. So a correlation is the correlation that's normally used as something called Pearson's R. And if we square the correlation, we can turn it into R squared. Why would we do that? Well, the R square value is what's used in a linear regression to show how well the model fits the data. And linear regression is a model. And it's very simple. You simply take the correlation and you square it. You multiply it by itself. Here we have a correlation of 0.859. When we multiply that by itself, we get 0.738. That means 73.8%. And it means 73.8% of the variance in one variable, the variation in one variable, can be explained or predicted from the other variable. So that's what we're trying to do in linear regression. We're trying to explain variation. In fact, we normally do that in statistics, generally speaking. But the way to think of this is to think of a Venn diagram where we've got two circles. One circle represents all the variation in vehicle weight, and one circle represents all the variation in horsepower. And they overlap by 73.8%. And if they overlap by 73.8%, we're saying this is how much horsepower, how much of the variation in horsepower can be explained using vehicle weight, and how much of the variation in vehicle weight can be explained using horsepower. So the relationship is a two-way relationship. Now, if you think about it, you can use this to try to estimate and figure out how strong a correlation needs to be in order to get quite a good R square. If you had a correlation of zero point 0.3, it's a fairly it's kind of borderline notable correlation, zero point 0.3. If you square that, you're going to get 0.09, 9%, and 9% overlap. 9% of the variation in one variable can be explained by the other. Zero point 0.4, correlation of 0.4, now you're getting somewhere. It's slightly stronger. Square that, it comes out as 16%. 16% overlap. Zero point 0.5, getting quite strong correlation now. 0.5, you're starting to get into the notable area here. That's 25%. Means the circles overlap by a quarter. 0.6, 36%. 0.7, so you need to get to 0.7, which is 49%. You need to be getting just above 0.7 before you're explaining half of the variation in one variable or another. So if you have an R square value of 0.49, you know that the correlation therefore must be zero point 0.7 between the two variables. So that's how the two things are related to one another. So this is how we measure the strength of the relationship or how well the model fits the data. But how do we actually express this linear relationship as a predictive model? How do we turn this linear relationship and say, I'm going to use this linear relationship and create a model from it? Well, it turns out the simplest way to explain this is to think about how long it takes to cook a chicken or some other sort of recipe. I really ought to come up with a vegan example of it, but this is how long it takes to cook a chicken. This is because somebody simply mentioned it to me one time and said, linear regression is a bit like when I asked my granny, how long it takes to cook a chicken. She said it was 20 minutes per pound plus 20 minutes per good measure. That happens to be pretty much the same formula that Delia Smith uses. And Julia Child used a different formula. She used 7 minutes per pound plus 45 minutes because she had different temperature settings and assumed certain assumptions about the chicken and how you were cooking it and that sort of thing. The point is that these are both formulae. They're little rules of thumb, but they're both formulae, and both of them happen to be the formula for a straight line. And the formula for a straight line, depending on whether or not you're a mathematician or depending on whether or not you're a statistician, can be shown as y equals mx plus c or y equals a plus bx. They're identical. Both of these formulas are identical. We've just changed the letters and changed them around a bit, but they're absolutely identical formulas. In the formula for a straight line, you have an observation and you have a coefficient and you have a constant added on to the end. There's always an extra number. So the 20 minutes for good measure here is the A, and the plus 45 minutes here is the C. And the 7 minutes per pound, that is the M here, 7 minutes per pound. The per pound is the X. And the 20 minutes per pound here is the B. 20 is the 20 minutes per. That's the coefficient. And the X is the weight of the chicken. So according to Delia Smith, depending on how you do it, if you've got like a 5 pound chicken, you're cooking it for 5 times 20 plus 20. So 120 minutes, 2 hours. We don't know what temperature that's set at. We don't know if it's a fan assisted oven. We don't know if it's the chicken being taken straight out of the fridge and it's cool or it's at room temperature. We don't know. But if you added those additional factors in to get a better estimate, you'd be doing a multiple linear regression and they would appear as different terms. Instead of just B1, you'd have B1, B2, B3 for the temperature, for whether or not it's a fan assisted oven, for whether or not the temperature, whether or not the chicken was served in put in the oven in a cooled state or not. But when we do a linear regression, it gives us the constant and it gives us these coefficients. And these coefficients tell us how much the variable is affected or how much the outcome variable is affected by the input variable. So how much longer you need to cook the chicken for every extra pound of weight. So it's really useful in that sense because it helps us model the data. So when I go back to looking at my earlier scatter plot here, and I look at percent of public healthcare, percent reliant on public healthcare against percent unemployed, and I put a line through it, what you'll find is that SPSS automatically gives you a linear regression equation. It gives you y equals mx plus c, or y equals b plus mx, or a plus bx, or whatever you want. This is saying if you want to predict, let's say, percent on public healthcare, and you know it's 10% people are unemployed, and you think, well, how many people are going public healthcare? You can look up the line here and just read it across and say it's going to come in about what, 24%, something like that, 23%, something like that. Well, that's basically because it's 10% plus 1.16%. So that's going to come in about 11.6% plus 10.1%. So it'll come in about 10.13%. It's probably going to come in about 23%, something like that, 22%, something like that. So that's what the formula is. So it actually gives it to you. Now, it's not going to do that for multiple linear regression because you can't show that as a scatter plot here because you can't show like 5 variables scatter plotted against one variable. But for a simple linear regression, where you just got one variable against another variable, it will give you the actual formula itself. So let's look at a demo of linear regression in IBM SPSS statistics. We're going to jump out here. We're going to look at our employee data set. I use this data set a lot because it's a really easy data set. Everybody understands it, and it's got a really nice mix of variables in it. And I'm going to try and predict people's current salary. Okay, so I predict people's current salary. If I go to analyze and go to regression, you'll notice that there's nowadays in SPSS, there's just a ton of different regression methods. There's so many different regressions. These are all forms of regression. Heckman regression, quantile regression, partial least squares, all different exotic forms of regression. The one that we're going to use is just linear. This is just your classic regression here, linear regression. I'll click linear here. And it has a dependent variable and independent variable. So the dependent variable is the thing you're trying to predict, sometimes called the target variable. I'm going to try and predict current salary. And I'm going to use people's beginning salary as a prediction, as my input variable for that. That's my independent variable. And I'm just going to run with the default settings at this point. And if I click OK at that point, it gives me the default settings. And what you see is it kicks out to me multiple tables. It gives me a title. It gives me some hidden notes here, which I've got just the system information about, how the procedure was run. We've got variables that were entered or removed. Well, it says at the start, no variables entered or removed. Just got the variable that's entered or removed is going to be beginning salary. That's only one. The method is enter. That means forced entry. We're going to force it in, whether or not it helps or not. Then we get model summary, which is our fit statistic. What is our fit statistic? Well, the correlation between beginning salary and current salary is 0.88. And if you multiply 0.88 by itself, it comes out as 0.775. So there's a 77.5% overlap in the variance between beginning salary and current salary. And then we've got something called adjusted R square. Adjusted R square is always slightly less than the R square value. It's what we generally tend to generally tend to quote when we're talking about the model itself. And it's a penalization function. It basically penalizes you for how complex the model is. It's always a little bit weaker. It's kind of like an adjustment for how many variables you put into the model. That's one of the things that affects it. But it's also taking into consideration things like the variation in the model. So we've got standard error of the estimate. We're saying, how much what the error is. On average, we'd expect this to be out by about $8,000 from one sample to the next if we take another sample of 474 cases. So this is the fit. This is basically telling us how well this model fits. Then we have an ANOVA table. An ANOVA table here is pretty much always significant unless you've just thrown in a random variable and there's no relationship between the two variables. The ANOVA table is basically saying, is this better than just taking the average? I mean, I could look at beginning salary here and go to beginning salary. I could right click on, sorry, on salary, on current salary, right click on that and say the average is, 34,419. There it is. It's just shown to me as a frequency table there. 34,000. Is this better than just saying, look, is this model here, is knowing beginning salary, is that better than just guessing everybody's got the average of 34,000? Well, yes, it is. It is statistically significant. We are rejecting the null hypothesis that it's no better than taking an average. So if the model's any way decent, if there's any sort of correlation really between significant correlation between the independent variable and dependent variable, you expect that to be significant, to be less than 0.05. And then finally, we get down to our coefficients table, and this is really the bit we're interested in. The fit is important, and the coefficients table is important. Fit tells us how well it fits the data. And the coefficient table tells us what the formula is for a y equals mx plus c or a y equals b plus ax or however you're using it. It shows us the constant value. It says let's assume the constant value is 19,000, 1,928, and the beginning salary is 1.9. It's got a coefficient 1.9. What that means is for every dollar of beginning salary, you get $1.9 in your current salary plus $1,900 on there. So that means if my beginning salary was $10,000, then my current salary would be $19,000 plus 1,900, so just under $22,000. Is that no, just under $21,000? Because just adding $2,000 on there. So it's a very simple thing here. This beta coefficient here, this is called a standardized version of this coefficient. It's put into standard units. What does it mean by standardized? It's actually standardized in the sense that this is the correlation. It's the same correlation again. Okay. It's actually a partial correlation. It shows us how much what the unique variation is, what the unique correlation is of beginning salary against the target variable of current salary, accounting for all the other variables that are in the equation. Well, there are no other variables in the equation, so therefore the correlation is exactly the same as the R value up here. And we can see that both the constant is significant, that is helping us predict the outcome, and that the beginning salary is also significant, that's also helping us predict the outcome. If I were just to do a chart of this, and just do a little chart here, a little scatter plot here, and I put in current salary, I'll put that. The convention is you put the dependent into the y-axis and the independent into the x-axis. You click OK at that point in time. And I could just put a line through that, see? Just put a line through that. And we get this little equation. Like, look at that. It's the same equation that we got beforehand. So it's like we're putting current salary against beginning salary. So there you go. And this is what our relationship looks like if we're illustrating it at that stage. So that's all straightforward and simple enough. But we know that there's a difference between people's beginning salary and current salary. Of course you'd expect your beginning salary to help you predict your current salary. What we don't know though is we don't know how long they've been employed. So obviously, the longer you've been employed, probably the bigger the difference there is between your current salary and beginning salary. So we've got this variable here, of job time. If I come down here to job time, let's see what are the smallest if I sort this in ascending order. Okay, the minimum value here is like I think 63 months for whatever reason. I don't know why, but 63 weeks or 63 months. Yeah. So this population, these people have been there for 5 years or so. And we would expect the relationship here between beginning salary and current salary to be to be closer together the less time they've been there. I mean, if it's only been there 3 months or so like that, you'd probably expect the same value. But we could pick up linear regression and we could add in job time. We could say months since hire and add that in. And we're adding it in using the enter method. That means forced entry. And now our R square value has jumped to, what was it beforehand? It was model summary 0.774. It's jumped a little bit. It's jumped a little bit to 0.784. It's gone up by a percentage, 78.4%. And if we look at beginning salary and months since hire, we can see that they're both significant. And we can see that beginning salary here is now $1.9 dollars. So it hasn't changed very much. A month since hire is $172. That's saying that for every month you've been there, you get an extra $172. That's what your time in the job is worth to you. And the constant is now a minus number. So we're actually taking $12,000 off that because we have to account for the fact that we've got these extra variables in there. Note that the correlation here now has gone from 0.882. It was previously it was 0.880. It's actually gone to 0.882. It's partial correlation. And this correlation is much weaker here. It's saying that there's only 10% of the variation in our adjusted R square here is contributed to by is accounted for by months since hire. Okay. Let's throw in another variable. It's now we're into multiple linear regression. Let's throw in another variable. Let's throw in education level in years. I'm going to put that in. Click OK. What's happening now? Oh, well, look, beginning salary here is dropped a lot. It's dropped from 1900 $1.9 or $1.90 for every beginning salary is worth what for your current salary is worth 1.689 $1.69 for every dollar of beginning salary. Previously is $1.90. Why is that? Well, because we've added an education level in years. And turns out educate for every year of education, that's worth $966. And now months since hire, that's worth $155 every month since. And we can see they're all statistically significant at this stage. And now look at the beta coefficients. These are getting weaker. So we're saying that, okay, beginning salary now not as strongly related, not bringing as much unique variation to the R square. The R square has gone up a little bit now to zero point 0.8. Months since hire is getting quite weak, but still statistically significant. And education level also weak, but still significant, still adding to it. So now our equation would look like this. It would look like beginning salary times 1.689 plus months since hire times 155.7 plus education levels and years times 966 minus 19,000. I think that's 19,986. So you'd be putting on a big minus constant at the end here. And that would get you an R square of 0.8. Now, statisticians at this stage would ask whether or not, that's worth it because, you got a much more complex model here than you had previously. But you've only gained about, 2.5% in terms of the explainability. So, one of the things statisticians do is they try not to overload the model with too many terms, too many extra variables in it. They try to get the biggest bang for their buck, if you like, out of the smallest number of terms. That's called parsimony, being parsimonious. Now, something you can do is you can actually add in these other variables like previous experience and months. I can actually add in a binary variable like minority, and I could add in age. I can get away with adding in a categorical variable like minority status here because it's a binary variable. It's like 0, 1. So you could add that in. And I can actually ask it to choose the variables, to choose which ones make a difference. So if I click forward here, it will actually build a much more complex model. Look at this. It built 5 models, one after another. Forward by changing the enter method, we now have beginning salary goes in first. Then it adds in previous experience in months. Then it adds in months since hire. Then it adds in education level in years. Then it adds in age, one at a time. And we can see the R square increasing each time from 0.77, 0.79, 0.803, 0.809, 0.81. So we only jumped by a tiny amount from 0.809 to 0.81, but we added in an extra variable. And we have an ANOVA table telling us that this is significant at each step. And we have a coefficients table here. Look at this coefficients table here. I can actually call this up and say I want to put the model into this the nested group here, and I can using nesting here I can say there's model one using beginning salary. Here's model two, beginning salary and previous experience in months. That went in next. Here's model three, months since hire went in. Look, that's gone in now. So previous experience. Here's model four, education level's gone in now. And here's model five. Now look what happened. I added in age. Age is just significant, but previous experience is no longer significant. Why is that? Well, because age and previous experience are related to one another. They're actually measuring in many ways the same thing. Obviously, the older you are, the more previous experience you have. So adding in age has made this non-significant. And this is one of the problems with multiple linear regression, that these two variables are probably correlated with each other. So you'd probably choose one over the other. So that's why we have forward method. And we also have another method, which is backward. Click backward. That backward is when you throw everything in and you just remove the variables which are no longer useful. So it starts out with every being thrown in, and then it ticks the variables out that aren't helping. So in the end, it ticks out previous experience. We have beginning salary, previous experience, education level, and age is what we ended up with. So previously we had what got taken out here. So yes, it took out minority classification, and it took out previous experience in months. Okay, so it's taken these factors out, and now we've ended up with a different model. So one model is a bit like trying to build, if you're using the forward method, it's kind of like trying to build a house of cards where you're putting one stack on top of the other without everything falling apart. And the other method's like playing Jenga, where you're trying to take out as much as possible and still just leave exactly the amount left that is actually contributing to it. Now, it turns out you can actually get linear regression to save scores for you. So if I choose this and I ask it to save the predictions for me, I can say, save the unstandard, save the predicted values for me. Look, it saves the predicted values for me. Here are the predictions. And I can change this and say, okay, look. And I'll make it dollars even. So it makes it easier for you to see. Look, there's dollars, there's the prediction. And there's the actual value there. 31,000. So I get rid of the decimals here. 31,000 gets 39,000. 21,000 gets 19,000. If I looked at the correlation between these two factors, the bivariate correlation, how much does the prediction correlate with the actual value here? Well, we know what that's going to be. It's going to be 0.90. How do we know it's going to be 0.90? Because when we looked at our fit statistics, look, there it was 0.901. Correlation, 0.901. Interestingly, it was actually higher with one variable in it. It's quite unstable. It's getting a little bit unstable here. See, the R score is actually going down a little bit. It's penalizing us for this. So model one was actually higher, so it hasn't added much to it. So, um, but yes, because that's what a correlation is. So, and if I wanted it to predict outcomes for me, there's different ways in which I could do that. I could go down to the bottom here and say, okay, well, look, I'll add in some cases here where we don't know the current salary. I could just add them on to the end here. And I could ask it to do a linear regression and save the predictions. And it would just save me a prediction for that case. Look, it saves me a prediction for that case, even though it's not there. So that's one way in which we can do it. The other way in which we could do it is we could we could tick linear regression here. We could ask it to save out the model as a file. So I could say save this as a file. I call it employee linear here. I'm going to override it and go yes. Save that as a file. Hit continue. And I've already got one in there. Click OK at that point. If I then just came along and created a new data set, I've got a new data set here where I don't know the outcome. So I'm deleting current salary there. I've saved my model as a XML file, and I can go to utilities here and go to scoring wizard, and I can find my XML file here and go next, and it will just match by the same variables that it used in the model. I'm not really interested in standard error, but it will produce the predicted value for me. Look at that, hit finish, and it produces, so I can apply the model to a new data set. So that's linear regression. That's one approach to it. This is how we can build up a model, how we can make sense of linear regression. There are lots of other things we need to know about linear regression. There are things called multicollinearity, which is where we look at the diagnostics around linear regression. There's lots of assumptions about linear regression. There are things like heteroscedasticity. There's all these plots you can do. You can do tests, special tests for statistics here for things like multicollinearity, which is to make sure that the variables aren't too correlated with each other. You don't want these variables here to be too strongly correlated with each other because then you're effectively measuring the same thing. You want the independent variables to be independent of one another. But that's for another session. Okay, we want to now move on to another type of regression. We want to talk about logistic regression. It's much easier to understand logistic regression when you've already seen linear regression because you've been introduced to the coefficients table and ANOVA tables and things like that. Logistic regression has similar sort of output. So with logistic regression, we're not trying to predict a continuous variable because linear regression can't predict things like the response to a marketing campaign. It can't predict whether or not you're a good or a bad credit risk. It can't predict whether or not a subscriber to Netflix is likely to renew their service or not. It can't predict whether or not a car is going to need servicing or whether or not a machine or a pump is going to break down. It can't predict whether or not how likely a patient is going to be readmitted to hospital within 30 days. And it can't predict whether or not a charity donor will switch to direct debit. And the reason why I can't predict those things is because they're not continuous outcomes. They're category outcomes. They're yes/no outcomes. Will he respond to the campaign? Yes, no. Will they renew the service? Yes, no. They're binary outcomes. And linear regression can't see binary. It can only see continuous values. So it would just give you a prediction of 1 or 0. Because they're not continuous numbers, standard linear regression won't work with it. And when the outcome consists of 2 categories, we tend to use binary logistic regression. When the outcome has more than 2 categories, we use multinomial logistic regression. Logistic regression gets around the limitations of describing relationships of straight lines by not using a straight line to describe a relationship. It uses a curvy linear relationship. And that curvy linear relationship is a special curve that you called the sigmoid curve. That means an S-shaped curve. It looks like this. And the way in which it works is if you imagine you had a little website, a little e-store where you were selling Apple iPhones. Okay. Why would somebody go and buy an iPhone from you if they could just go and buy one from Apple directly or from their internet service provider or whatever? If you're not offering a discount. So we can assume that if you're not offering a discount and you're selling iPhones, that nobody's going to, the likelihood of anyone buying from you is pretty much 0. But as you start to introduce a discount, say 5% discount, 10% discount, the probability of people responding to your offer and actually visiting your website and buying something starts to increase. And let's say at a 50% discount, you get 50%, people are 50% likely to buy from you. If you have a 100% discount where it's free, then everybody responds to it. Obviously, if you're giving away free iPhones, everyone's going to do that. So this is how logistic works. It doesn't work on the basis that, it's just a straight line. That there's this way to try and discriminate between 2 conditions. And that's why it's an S-shaped curve, because it's trying to discriminate. It's a curve that discriminates between a zero and a one condition. Okay. But the question here is there is a special formula that converts these values into probabilities. These values are the values which you're going to get out of the regression equation that you're going to do when you do your logistic regression. So the special formula converts the values of predictor coefficients on the x-axis to values on the predicted probabilities on the y-axis. So you're going to get these numbers when you do your logistic regression. And these numbers you can put through a probability, you can put through a little formula. That formula is called the link function, and it converts them to probabilities for you because it's not a straight line. The numbers can't be interpreted in the same way that you would interpret linear regression. You can't say, for example, for every $1 increase in your current salary, you are 0.1% more likely to buy a product or something like that. It doesn't work like that because that doesn't describe the relationship between this axis and this axis using this sigmoid curve. The formula happens to be 1 over 1 plus e to the power of minus z, where e is the value of the exponent, a bit like pi, and minus z is in fact the y equals mx plus c. So, I mean, I just know that because I've been doing it for years. But, basically, what that does is it creates a probability values for you. That means it creates a number that goes from 0 to 1. And the downside is, the bad news is that these numbers are going to be really hard to interpret. I mean, the linear regressions produces coefficients which are really easy to interpret. 20 minutes per pound plus 20 minutes per good measure. Logistic regression does not produce numbers or coefficients which are easy to interpret. And the reason is because the numbers it produces are not the actual values. They are the log of the odds of the values. That's what it is. The logs, they're logged values. And people find it very hard to think in terms of odds, never mind probabilities, but think in terms of odds, and never mind the log of the odds. And they show how what a 1 unit change in the variable, how much that has an effect on the log of the odds of you being in the category. Now we'll see what that looks like when we actually run this. So let's jump out and we'll go to a different data set now. And we've got a data set here called News Channel for Logistics. So this is kind of an old data set. Let's just close down the output here so we don't have output in the background open. Just close that down. Don't want that open, so I want to start from scratch. And it's an old data set. Let's imagine it isn't a news channel. Let's imagine it's a news app. Okay, so you got a news app, and people got to pay for the news app, whether it's like say, Times or the Financial Times or the Guardian or something like that. So who's going to sign up for it and who's not going to sign up for it? Well, let's just look at the data set here. If I right click on it, it's about 50-50 here, which makes it nice and neat for descriptive purposes. As an example, it's nice and easy because it's like 50-50, so it's kind of easier to get your head around. But of course, a lot of times when you're using logistic regression, it's not going to be 50-50. It's going to be something like 20%, 80%, or something like that. It might be 10%, it might be 90%, it might be 5% people fall in one group and 95% don't. So if you're trying to predict, as logistic regression is used a lot with things like debt modeling, trying to predict whether or not somebody's actually going to pay you back. Most people pay you back, but you're trying to figure out what the risk is. So, you'd find 95% of people are in the yes group and only 5% are in the no group. So you need to be aware of what we'll call the baseline probability is because we're trying to predict a model which shows the likelihood or probability of somebody paying you back and not paying you back. If they say there's a 10% chance they won't pay you back, you might think, well, that's not too bad. There's a 90% chance they will. But if the baseline's 5%, it means they're twice as likely not to pay you back. So, if there's only a 10% chance somebody's going to be readmitted to hospital within 30 days, if they get a probability of 0.3, then there's a 30% chance they're going to be admitted to hospital within 30 days, which is still less than 50%, Still means they're probably not going to be readmitted to hospital within 30 days, but it's three times the base. So you have to know what the baseline is before you start, because otherwise you're not going to be making sensible interpretations of what is risky or what's a high likelihood relative to the average. So if we go to regression here, we're going to go down to binary logistic, and I'm going to pick up my dependent variable here, which is accept news channel offering, which it just has these two values, yes and no. One is coded as yes and zero is coded as no. And I'm going to pick up these variables here and chuck them in. Now, unlike unlike logistic regression, unlike linear regression, if you have a category variable here, you might have something like social class, let's say. Social class, you're going to throw that in there. Could have four or five different categories in it. How are you going to work with that? Well, it turns out you can tell it that it's a categorical variable. I'm going to pretend that gender is like social class here. I don't actually have to do this because gender's already only got two values, 0 and 1, and that is in mathematical terms and statistics, that's like a continuous variable anyway. But if it was something like, region or something like that, or what current newspaper they currently read, made like five different newspapers. What you do is you'd select you do call something called dummy coding, and you select one category, and what it does is it shows you the coefficients of the effect of not being in that category. So when we see the results here, we're going to see the effect of not being in the first category on your likelihood to accept a news channel. What does that mean? Well, what's the first category? The first category is male, and the second category, the next category is female. So I could say, well, I'm gonna leave it like that, first category male. So it's going to show me the effect on the log of the odds of being a woman on accepting the news channel. That's what it is. So it's basically saying compared to being a man. So that's what the reference category is. So if we click OK at this stage, we run it, we're going to get different output than previously. First of all, it tells us how the dependent variable is coded, 0 and 1, and it tells us how it's coded internally. Well, it's coded gender variable 0 and 1, so it's coded 0 and 1. We're happy with that. That's fine. It says you got 5 missing cases here. That's fine. 442 cases. And it starts off, and instead of giving us an ANOVA table, it gives us a classification table. A classification table here is basically saying, look, if I knew nothing about this data set and I knew nothing about all of the other variables and all the other factors in it, and I had to try and predict, which group somebody's going to be in, whether or not they're going to accept the news channel or not accept the news channel, I'm going to predict that everybody's in the no group. Why am I going to predict that? Well, because there's 224 of them. And there's 213 people in the yes group. So, it's marginally more likely they're going to be no than yes. So this is your baseline. Okay. And this is 51% overall correct. So that's what you're trying to beat. The point is that that's saying what you're trying to beat. You can imagine if this was like, not only 10% of people accepted the news channel, 90% didn't. Then the baseline, everyone would be predicted to be not accepting the news channel. And the percentage correct would be 90% because, that's what you should be betting on. You'd be trying to beat that. You'd be trying to come up with a model that was more accurate than that did a better job. And the next thing it does is it shows us the variables in the equation. And this b value here is the log of the odds of you being in the yes group, being yes, I'm going to respond, I'm going to buy this, I'm going to buy this news channel. If you're just using the constant, and it turns out that equates to 51%. If I took this number here and I put it through my special link function, my little formula, 1 over 1 plus e to the power minus z, this would be the minus z. I'd actually be raising e to the power of 0.05. What it would do is it would give me a number, and that number would be 0.513, which would be a probability of 51.3%, basically, which is exactly the same. So it's just saying, and it's also testing it and saying, is this better than a wild guess? Well, it turns out it's not better than a wild guess. Why is it not better than a wild guess? Because it's very, very close to 50-50 anyway. It's so it's such a tiny difference that it's not better than a wild guess. So the constant isn't really even doing much work. At this stage, it says, Okay, here are the variables that are not in the equation. And I haven't added them yet into the model, but I can tell you right away that education at this stage is not going to make a significant contribution. And that hours spent watching TV per day is not going to make a significant contribution. But gender and age do make a significant contribution. So now it's doing some tests and it says the block, a step block and model, well, everything's getting entered at the same time. So these values are all the same. We're not entering them different steps. We're not entering them different blocks. And we're not creating separate models. They're all one model, one block, one step. So it's just saying when we enter these variables, we're forcing them in. They will make a significant difference to the accuracy of the model. They will increase, they will be better in a wild guess. And because it doesn't have an R square value, because it's not a continuous situation like what linear regression has, it gives us what we call pseudo R squares. So we get Cox and Snell, that's a pseudo R square, 0.147, 14.7%, and Nagelkirch R square, 0.19, but 19%. They're pretty weak. They're always pretty weak. Don't worry about that too much. But it doesn't mean it's a bad model or anything. God, they're always pretty weak because they're trying to kind of the pseudo R squares. This number here is this really abstract number, which is minus 2 log likelihood 536.117. That is again a very abstract number, but basically the smaller that number is, the better the fit the model. So if you want to compare one model to the next, whichever one has the smaller minus 2 log likelihood generally tends to be the one with the better fit. And then it shows me what the classification table would look like if we were using the model. And it says if you use the model, then 68.8% of the time you will predict the no group correctly. That's the observed. And 62% of the time you will predict the yes group correctly. And if you were to look at the equation, the variables in the equation, you get a b value, you get an exponentiated b value. I'll come to that in a second. But you can see some of these variables here are not statistically significant. At this stage, hours spent watching TV per day is not statistically significant. I'm going to run it again. I'm going to take out hours spent watching TV per day. Take that out. Let's run it again. So it's easier. The remaining variables are now significant. Interestingly, let's added them in. After it's added them in, on their own, education in years wasn't significant, I don't think. But yeah, education in years was not significant at this stage. But once we've added it in, it's become significant. And what we have is this exponentiated b value. Well, if we take the exponentiated b value, what that is doing is telling you how much an effect a 1 unit change has in the odds. And it's saying that because our reference group here is male, it's saying that, and the b value is a minus number, it means that you're reducing the odds in this gender group here. So it's basically saying if you're a woman compared to being a man, the odds of you accepting the news channel are reduced because it's a minus number. And how much are they reduced by? They are halved, 0.47. The odds are halved. The odd, not the probability, the odds of accepting the news channel are halved if you're a woman. For every 1 unit increase in education level, the odds increase by 1.1. But education level is you could have 10 years education, you could have 20 years of education. So that's showing each step. So, let's say 10 years education could be increasing the odds by 10, by a significant amount. Same with age. Every 1 unit increase in age increases that. What does this model actually produce for us? Well, if we look at logistic regression and say, go to save, notice that I can save out as an XML file, just like I did with my linear regression earlier on. If I click continue at this stage, it saves the probability of you being in the yes group and the probability of you, the probability of being in the yes group and its predicted group. So it says, look, there's only a 18.9% chance you're going to be in the yes group. So I'm going to predict you be a no. There's a 75% chance you're going to be in the yes group, so I'm going to predict you be a yes. There's a 52% chance you're in the yes group, so I'm going to predict you be a yes. There's an 83% chance you're in the yes group. I'm going to predict you yes. Are you in the yes group? No, it's an error. Look, it's a mistake. Yeah. Now, it turns out that this probability value here is what people work against. They say, look, they pick a margin. They say, look, anybody with a value above 0.3 or anybody with a value above 0.2 is too risky for us, you know, because you're not really you're not really that concerned about the predicted group because the predicted group's just based on those who have a value higher than 50%. You know, if you had a value of 0.49999, you'd be predicted to be a no. If you have a value of 0.500001, you'd be predicted to be a yes. It's just arbitrary. And for that reason, you can actually control the threshold value. You can actually go into the options here and say, you know, I'm going to change the classification cutoff here to zero point 0.4 because that reflects my group cutoff. You know, 40% of people belong to one group and 60% belong to another. And as a result of that, people tend to use, you know, if you're looking at predicting whether or not somebody is going to be lent money, and they do use logistic regression for credit scoring, they're not basing it on whether or not you got a score above zero point 0.5. They're basing it on whether or not you got a score of above zero point 0.1, you know, whether or not there's a 10%, whether 10% chance you may not pay them back. So this number here is the key value. This is the number, this is the risk, this is the likelihood. If you were trying to predict people who are going to respond to a mail shot and there's only a 1% chance they're going to respond to an offer, you know, a probability of point one is 10%. That means they're 10% as likely to respond to the offer. And you might well select anybody with a score of a zero point 0.1 or higher. So you have to really think sensibly about, what your baseline probability is and what it is that you're trying to predict. Okay, so that takes us through logistic regression. You can see it's very different from linear regression because the relationship is non-linear. It's a little bit more obscure. And there's lots of extra information out there about logistic regression, but bear in mind that this is only one type of regression method. There are many other types of regression methods. Linear regression is a classic type. Somebody asked, I think, earlier on, why do we square the correlation? Well, we square correlations because they turn it into R squares, and R square is what's used as a fit in linear regression, and it's a way to turn it into a percentage so that we can say what percentage of variance in one variable is explained by the other variable, and it is often more intuitive for people. There are some additional resources here, such as how to model nonlinear relationships. We've got some videos on that. And in the next webinar, we're actually going to be looking at linear regression again, but we're going to be looking at like a slightly more sophisticated series of events about linear regression. We're going to look at moderation analysis, mediation analysis. If you're really interested in modeling data of linear regression, then I would urge you either look at these videos or attend the next session because we're going to be using a special plug-in tool that you can get for free called the process tool. And it really helps us work out, the relationships between the variables in the linear regression and do a much deeper analysis. But there's other stuff you can click on here. You can look at stuff about the correct statistical test, how to interpret significance tests, and a little blog series called Eat Your Greens, which looks at basic statistical testing and procedures. Just a grounding in SPSS statistics. Bear in mind we've got loads and loads of different videos on YouTube about prediction and about other forms of regression. As I said in the last session, you should be aware we have a chat SPSS chatbot which you can sign up for free from our website. Just go on to support and chat SPSS. And you should be aware that we have our own series of training materials. They're free to Smart Vision customers, or they're available for purchase for non-customers. People who are not customers can sign up, can move their licenses to us, and we'll look after the licenses for them. We offer training and consulting services. We offer free technical support, and we offer no strings attached technical business advice related to all analytical activities. You can buy your software directly from us, often with discounts, and we have our own web store. In the meantime, thanks very much for logging in. And we look forward to you logging in again in the next webinar if you want to join us then. Thanks very much.